welcome back to the video series for Geography 300, Geographical Data Analysis at WVU. We're continuing with our discussion here of geographically weighted regression, now looking at some of the limitations. Now, I'll be focusing on three limitations, the first two of which are actually related to each other. Regression is always, shouldn't say always, but usually better if you have more data. Just a general principle. Having more data tends to be better than having less data. But now that I am just looking at a neighborhood, for each individual small regression, remember, we aren't using the full 55 counties. We're now looking at, say, 8 or 10. That means there's a small sample size. It isn't necessarily as reliable by itself because of that small sample size. And in effect, the smaller your sample gets, the harder it will be to actually be certain you have a meaningful relationship when you're running your regression. At the most basic, most obvious example, if I have a regression scatter plot with 2 points, I can put a line perfectly through that. At those 2 points, it will be a perfect prediction. R squared is 100%, R squared is 1. But that's true for any single 2 points. It tells me absolutely nothing about this relationship. So having a small sample size is a limitation. Related to that is something called multicollinearity. And it's a big word, I'll put it up here. This actually comes up a lot. And it's a problem where your independent variables are actually not independent of each other. And that can be an issue, especially in GWR, because of these small sample size. So to take probably a really obvious example of multicollinearity, I have seen people suggest, I don't know that it's actually true in practice, but I've seen people suggest that counties that voted for a president are more likely to get federal relief dollars from that president. So, okay, we might say, okay, to take the time span of 2017 to 2021, or I should say January 2021 to 2020, the administration of President Trump, the last full president, why I'm picking that particular president, we might say the percent who voted for Trump and the percent who voted for Clinton in terms of did they get federal relief dollars. Percent for Trump and percent for Clinton are in no way, shape, or form independent of each other. And what it ends up happening is the regression model, the computer, won't be able to tell, even if there is a relationship there. It cannot say, is a place getting rewarded? Is it getting more federal relief dollars because it voted for Trump? Or is it penalizing the places that voted for Clinton? Which independent variable could be the driving factor? In this case, it cannot tell between them. And if it's in a very extreme example, you end up getting divided by errors, problems, and values becoming infinity, and the computer really just doesn't like that. All because our independent variables were too closely related to each other. How this relates to GWR? When we are doing our local regressions, even if statewide, nationwide, across the entire study area, our two variables are sufficiently independent to work together. But even if there is one neighborhood where they are too closely related, the whole thing will break down. So you're much more likely to get errors because of multicollinearity with GWR than you are with regular regression. And you will almost, don't panic if you do. It will not say multicollinearity, as I'll have in the lab. It will tell you severe model design problems. Probably means this. Not guaranteed, but it probably means this. So those are the two issues with sample size. There's a third issue with GWR. And it's the problem that we have a lot of tests that we're running, and they're not even truly independent of each other. So the first part of this goes back to how we interpret our p-values. We pick a threshold based upon how willing we are to be wrong. So that p-value, 0.05, what that means is when I go and I say there is a relationship here, when I go and I reject the null hypothesis to say there's a relationship, there is only a 5% chance that I'm wrong when I say that. That's where the 5.05 comes from. But, okay, now what if I'm doing 55 counties? 55 different counties, and there is a 1 in 20 chance for any of them to say there's a relationship here when there really isn't. 1 in 20 when I'm looking at a 55. Now odds are I might have 3 counties that it's going to say there's a relationship, but it really shouldn't be. So now we have, because we're doing many tests, the multiple testing problem, as it's sometimes called, so it means I have an increased chance of a false positive or several when I say there's a relationship, but there really isn't. On top of that, our tests are not independent. To say out of 55 counties, I should expect 3 to give this kind of error. Okay, that's assuming they're all independent. But if you think back to the circles I was drawing, on the map in the previous video. The neighborhood for Preston County and the neighborhood for Mon County have a whole lot of overlap. So those regression tests aren't really independent of each other in the first place. So that means if Preston County's statement, there's a relationship here, was a false positive, now there's a really good chance that I'll have the exact same conclusion and the exact same false positive status for Mon County, because there is so much overlap in the neighborhoods that created the false positive for Preston County. It's basically the same data, with only maybe 2 or 3 values changed. Okay, so this could really start to be an interpretation problem. I'm not going to have as much confidence. There are ways to resolve this to a certain extent. I'll present one of them, which is, in a sense, the most severe, which is, in a sense, correcting that decision threshold. And so instead of it being, so use alpha divided by the number of tests. So this is, as I said, if anything, it's overcompensating, but that's probably not the worst thing in the world right now. So 0.05 becomes 0.05 divided by 55, which I'm not sure exactly what that's going to be. But that's going to, just to pick something, whatever that is, it might be say 0.001 or 0.0001. It's going to be much less than 0.05. And I now have a much lower threshold. And I'm going to use this low threshold in my decision making to say, for my GWR, are these local values actually significant? Well, this has been suggested. To be honest, in practice, I don't see it that much. And there can be different arguments back and forth, whether you should do it, whether you shouldn't. The main thing is to be aware that this potential for a false positive coming up in your data increases by doing a lot of small regression tests like GWR does. So those are these limitations. The next video will look at presenting geographically weighted regression. Thank you for watching. As always, feel free to ask questions in class or by email. I'll see you at the next